Hello, dear friends. Today we will consider one comment made related to our webinar on global cooling from plant transpiration. And this comment was made by Ed, who thinks that it is relatively straightforward to estimate relative influences of albedo and transpirational cooling on global temperature. So what Ed was saying, I was suggesting that the albedo issue should be clear, simply because despite the heating of the leaf surface, forests are cool, and lighter surfaces like deserts are hot in the sun. As a result, we conclude that evaporative cooling is more powerful. Or, as Antonio Nobre reported in a lecture, that a clear-cut area in the Amazon was 10 degrees Celsius hotter than the forest nearby. So, albedo is clearly a minor phenomenon. That is to say, we know that transparent surfaces are cool despite they are darker. Can we conclude from this that transpiration definitely is a stronger effect for global temperature than albedo? So I will argue that things are more complicated, and that is why our webinar was like 2.5 hours and not 5 minutes showing these obvious things. And why is it more complicated? The matter is that transpiration does capture latent heat locally, but upon condensation, all this heat is released back and it increases air temperature. And with this heat, the descending air can warm other locations. So it makes one location cooler and another one warmer. And we have to weigh these two opposite effects. And let me give you an example that this is real. We all know that condensation is most intense in hurricanes, okay? So what is a hurricane? We can see this picture at the bottom of the slide. So it is a relatively big area with ascending air motion with condensation, so we can see clouds, right? But at the outskirts of this core region, there is descending air motion because the air cannot just go up, it also goes down. And here on the left, you can see the graph from our paper in 2017, which shows how precipitation is distributed over radius from hurricane center compared to its mean value in the absence of hurricanes. So these black circles is precipitation in the absence of hurricanes, and these red circles is precipitation in the presence of hurricanes. And you can see that there is an area like around 1,000 kilometers where precipitation is suppressed. And it is suppressed because here we have this descending air motion. So the air descends, and this air brings with it latent heat that was released in the upper troposphere. And now let's take a look at another picture here to the right. It is from Montgomery et al. And colleagues, 2006. And here we can see the distribution of temperature along the radius. And so this vertical is height. So this is surface, and this is 2 kilometers above the surface, but that's not so important. We are concentrated on the surface. And this green line and this blue line, which coincides with green line, is the outskirts, the furthermost radii, and like 1,000 kilometers, and we can see that here the temperature is higher than it is at the hurricane core. So here where there is descending air motion, there is higher temperature than where there is ascending air motion, because the circulation in hurricanes is so strong that the heat has no time for all the heat to be released to space. Otherwise, hurricanes would be radiating as stars. So part of it goes with the descending air motion and warms this area that where this descent occurs. And so we can see that we cannot just say, oh, transpiration made this local surface cooler, and so it is more powerful than albedo. No, we need to study what happens with this latent heat. And as I said during the webinar, the longer this warm air stays in the upper troposphere, the more time it has to radiate this extra heat, this latent heat, relatively unimpeded to space. And so the more pronounced the global cooling is. So in order to ensure global cooling from transpiration, we not only have to capture latent heat where transpiration actually occurs, but we also need to get rid of this heat from the upper atmosphere, such that most absorbers are beneath this radiative layer. Okay, this is what, and that is why we need to somehow calculate this effect quantitatively. We cannot just do it in qualitative terms. So that's the complication. So that's it for today. You can find further information in our webinar and also in our recent preprint, which summarizes what we have to say on this topic. Thank you for your attention today. Bye-bye.